So the next thing we're going to do is move into section 1.3 in the book, well, more or less section 1.3, and we're going to talk about some properties of limits. Basically, the idea is if I know how to find some limits, and we do know how to find some limits from graphs and tables of values, we're going to see how to combine them, how to find sums and differences and quotients and all that good stuff. So there are 6 properties of limits, and pretty much I'm just going to sort of list them here, and then we'll take a look at a worksheet and kind of see how to apply these things. So first of all, if we say that the limit as x approaches c of f of x and the limit as x approaches c of g of x exist. These properties are only going to work in cases where the limits exist. If the limits do not exist, these properties are off. Well, our first property, and again, just like the first day with taking notes, if I'm going too fast, please pause the video and get caught up. The first property is our sum or difference rule. Which says, if I want to do the limit as x approaches c of the sum or difference f of x plus or minus g of x. If I want to add or subtract 2 things inside a limit, well, really all I have to do is the limit as x approaches c of the first thing, plus or minus the limit as x approaches c of the second thing. This is going to equal the limit as x approaches c of f of x, plus or minus the limit as x approaches c of g of x. If I have a sum or a difference inside my limit, I can separate this into 2 different limits that I'm adding or subtracting. We then have a scalar multiplication rule. Which says the following. If I want to do the limit as x approaches c of some scalar, remember which is just a fancy word for constant, times my function f of x, well, I can take this constant out front before my limit and say b times, let's just do the limit as x approaches c, of that f of x piece. If I have a constant inside my limit, I can just move that out front. Well, then I have a product rule. My product rule says the limit as x approaches c of f of x times g of x equals, well, it's exactly what you probably thought it was going to be. If I have a product inside of a limit, I can do the limit of the first one times the limit of the second one and get the limit as x approaches c of f of x times the limit as x approaches c of g of x. I realize that these properties may seem kind of obvious and stuff. One reason I do need to go through these, though, in detail with you guys right now is so later when we look at derivatives and integrals, we'll see that these properties don't necessarily apply, and we kind of want to have something to be able to compare them to a little bit later. So for right now, product with 2 limits, let me try that again. The limit of a product is the product of our limits. Next, we have a quotient rule, which says that the limit as x approaches c of f of x over g of x equals, well, yeah, exactly what you thought. The limit as x approaches c of f of x over the limit as x approaches c of g of x. Well, actually almost. Almost all the time. There's one slight problem that I could have. What would make this not true? What would give me a problem with this? Hopefully you were thinking, well, if that denominator is 0, this property is only going to hold if the limit as x approaches c of that denominator function does not equal 0. Next, we have the power rule. Which says if I want to do the limit as x approaches c of some function raised to a power, I can take my limit as x approaches c of my function f of x, get an answer, raise the answer to the nth power. One more, and then we'll start applying these. We have a composition rule. Which says if I want to do the limit as x approaches c of f of g of x, hopefully you remember that the term composition in math means one function inside another. If I want to find this limit, well, I'm going to start on the inside. I'm going to take the limit of the inside function, and then just plug that answer into my outside function. This is going to equal f of the limit as x approaches c of g of x. I'll find the limit of that inside function, plug that answer into my outside function. Well, actually, sort of. I do have to add one little qualifier in here, which isn't going to matter so much right now, but will matter in a couple days. This is only going to apply if our f function is continuous at whatever this limit happens to be, and if it's not, we'll deal with that a little bit later. If f is continuous at x, not at x equals, at the limit as x approaches c of g of x. So we'll take this limit, we'll get a y value. As long as my f function is continuous at whatever that value is, then I'm allowed to use this property. Again, we're not going to worry too much about that right now. We'll see what happens if it's not continuous in a little bit. So I'd like to take a look at that worksheet titled Section 1.2 In-Class Practice with Properties of Limits. We have a graph on the top of the page with the function f and the function g, and I want to use my properties of limits to evaluate these limits that I see over here, and I want to try to do this in a fairly formal way. Here's what I mean. I'm going to get you started on a couple of these, then you're going to try some on your own. In number 1, well, I want to do the limit as x approaches 2 of some new function which is defined by f of x minus g of x. I have my properties of limits, in particular my sum and difference rule, in particular the difference rule, that says I can rewrite this as the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x. Now, all I have to do is figure out this limit, figure out that limit, and subtract the answers. This is what I mean by how we can apply the properties. Okay, well, the limit as x approaches 2 of f of x, here's my f function. As my x's are getting close to 2, looks like the y's are getting close to 2 as well. The limit as x approaches 2 on the g function. Okay, here's the g function over here. As my x's get close to 2, looks like that's getting close to 0. So I'm going to do 2 minus 0, and I'm going to get 2 for that final answer. As for the work, yeah, I really do want to see how you're applying the properties. So show me this rewriting step, then show me how you're evaluating each, and then give me the final answer. Number 2, we have our scalar product property that says I can take that 3 and move it out front and turn this problem into 3 times the limit as x approaches 4 of g of x. Okay, well, let me go do that limit as x approaches 4 of g of x. Here's my g function. As x is approaching 4, looks like my y values are approaching 2. So I'm going to say 3 times 2. Whoops, no, I'm not. That's not my final answer. I'm going to say 3 times 2, which, of course, you're really going to say equals 6. I'd like to see if you can deal with number 3. You're going to have to apply two different properties, but I don't think that should be a big deal. See if you can rewrite it, and then see if you can figure out the answer. Say this is the limit as x approaches -2 of f of x plus, I'll move the 5 out front before the second limit that I'm about to write, so 5 times the limit as x approaches -2 of g of x. Okay, let's figure these out. Limit as x approaches -2 of the f function. Looks like my y's are getting close to 1. Remember, it's a limit, not an f, so I don't care about that point up there. I'm going to say 1 plus 5 times limit as x approaches -2 of the g function. That looks like -1. I don't know what I just wrote. Let me try that again. This is going to be 1 plus 5 times -1. 1 minus 5 should get -4 for an answer. Please go try problem number 4. By my quotient rule, I'm going to say the limit as x approaches 3 of f of x over the limit as x approaches 3 of g of x. Let's go find these. As I approach 3 on the f function, I'm getting 1, 2, 3. Okay, it looks like my y's are approaching 0. As I approach 3 on the g function, this one over here, looks like my y's are approaching 1. So 0 over 1, I'm going to get 0 out of that. I want to try number 5 with you just because the composition stuff's a little weird notation-wise, maybe. Our composition rule says as long as continuous things check, and we'll kind of see that as we go about doing this problem, I'm allowed to move this limit inside my outer function. So I'm going to say this is g of whatever the limit as x approaches 1 of f of x is. Okay, limit as x approaches 1 of f of x. That looks like 2. So this problem becomes g of 2. Before I go on, I just need to make sure my g function is continuous at x equals 2, because if it's not, I'm not allowed to use this property. But it is. That's good. What's g of 2? What's the y value right there when x equals 2? 0. See if you can try number 6. Again, uses two different properties, but I think you can figure this out. Okay, I'm going to say the limit as x approaches 1 of f of x. I'm going to square that limit. I'm going to multiply that answer by the limit as x approaches 1 of g of x. Okay, limit as x approaches 1 of f of x. That looks like 2. So I'm going to do 2 squared times limit as x approaches 1 of g of x. Oh, okay, that's a problem. There is no limit there. That limit doesn't exist. Doesn't really make sense to talk about the problem 4 times does not exist. If any part of a product here doesn't exist, your overall limit does not exist. So I have to say my answer for number 6 is does not exist. Let's try a few of these numerically. Turn that sheet over to the back. We don't have a graph. We just have two limits that I'm telling you over here. Limit as x approaches c of f of x equals 9. Limit as x approaches c of g of x equals 5. And from just those two pieces of information, we're going to try to do everything on this sheet. You know what? See if you can do number 7. I think you can figure out what to do in number 7 without my help. Try that one. I'm going to rewrite this as the limit as x approaches c of g of x minus 2 times the limit as x approaches c of f of x. Okay, limit as x approaches c of g of x, I know that that's 5. Minus 2 times limit as x approaches c of f of x, I know that that's 9. 5 minus 18, I believe, should be negative 13. we didn't have a property that that really talked directly about square roots. But we still can figure out number 8 because hopefully you remember a square root is just like a 1/2 power. So really, we're using the power rule here in number 8. See if you can deal with number 8. I'm going to say this is the square root of the limit as x approaches c of f of x. That limit is 9. Square root of 9, or again, if we're thinking power rule, really like 9 to the 1/2, but it's the same thing. Square root of 9, you're going to get 3. Please try number 9. So by my quotient rule, I'm going to write it like this. The limit of the quotient is the quotient of the limits. I'm going to get 9 over 5. Just leave it as 9/5. Give me fraction answers anytime you can over decimals. One more. Try that last one. See what you can do in number 10. Either another power rule or a composition problem or whatever. I'm going to do the limit as x approaches c of f of x. I'm going to get my answer, and then I'll raise that answer to the 3/2 power. Okay, so what's this limit? This is 9. Raise that to the 3/2. Hopefully remember a 3/2 power means let's take the square root and cube it. Denominator is the root, numerator is the power. By the way, you could do your power first, and then your root 9 to the 3rd, then take the square root. But you're not going to have a calculator for this on our test nor on the AP exam. So let's make it easier. Let's do our square root of 9. Then let's cube that. This is 3 cubed, which is 27, which is easy to do by hand. 9 to the 3/2, 9 to the 3rd. I know 9 squared is 81 times another 9. I don't really know, and then we'd have to take the square root. Do your roots first. It makes the number smaller and easier to work with.